introduced to VMware. I've actually known them for a very long time. We used to be basically office mates in graduate school. And we've been doing lots of really amazing work in NLP, and I'm really excited to hear about it.
Thanks. Yeah, so in grad school I used to actually work on reinforcement learning. I've since diverged off, and I think mostly all about language and language understanding now. So it's very fun for me. I really appreciate the invitation to come to this workshop to sort of learn more about some of the more recent stuff, learn a bit more about active learning. And I hope I can convince you that a lot of the stuff I'm talking about is very relevant, even if I'm more on the applied side and less on the theoretical side these days. And I should, before I forget, acknowledge these folks down here, including 3 PhD students and who are currently still at UW, and Mike Lewis, who is a postdoc and is now at FAIR here locally. So what I want to talk about is some issues in building parsers that are motivated by doing a relatively detailed semantic analysis of a text and trying to get them to actually work in general. Okay, so we're going to have to pull out all our tricks and think about what kind of supervision could we get, how could we learn from it, and how are we going to make these things actually work. To put a little of this in context, when I think about semantic analysis in my research group, we do lots and lots of different application domains, and I'll give you a little bit of overview of some of them. But at a very high schematic level, what we want to do is get a piece of text as input, usually a sentence, run some sort of parsing algorithm on it, and produce some representation of the meaning. Okay? We don't actually know how to represent the full meaning of any input text, but we can represent enough of the meaning that we can hopefully do the things we need to do in application. And so the way we'll do that is we'll actually use that meaning representation to do something, and we'll measure a response. And if we're doing well according to that response, then we must have been understanding the meaning of the text. So let's look at some specific examples. If you're building a natural language interface to a database, where one application area where there's been a ton of work for this style of work, your intermediate representation, maybe it would be more formal, but it's, in some sense it's equivalent to something like a SQL query. And then you're doing a good job if you can answer questions correctly. Okay? In a robotics setting, nothing anywhere near as fancy as the robotics talks you saw through the day today. But in simulation or some other setting, we've done some work where you get an instruction and you need to map it to a program. And that program should run correctly on the robot and have it do what you want. So if you tell it to go somewhere, it should actually get there. Okay, very simple kind of setup. More generally, you can apply this to all kinds of problems in natural language processing. So for example, in information extraction, if you actually understand the facts being claimed by a sentence, you could convert them to some sort of tuples that could be asserted against a database or a knowledge base. And if you're only ever adding correct facts, then you must have understood the language well, right? And ideally, you should add them all also. Okay. And in this style of work, the real challenge is all of those things I was telling you, there are a ton of decisions that need to be made. And don't try to, I've purposefully grayed out this background here, but it is an actual analysis of the kind of models that we can do, but don't feel like you need to unpack it. But the key idea here is that what we're going to have, is some amount of information, syntactic and semantic, that are coming from each of the individual words in the sentence. And then it's going to be combined compositionally to build up bigger and bigger representations. And then that final representation is going to be some sort of semantics that we can feed along through and do our task on top of. Now the trick, of course, is that getting data for these really detailed analysis is super painful. It's not just a little bit painful, it's super painful. And so the real game here is how much can you do latent variable learning and how much can you learn from these end responses. So for example, if you could learn just from the answer to the question, where there's literally sort of exponentially many possible analyses that you could have had, you don't know which one is the right one, and somehow you need to sort that out and actually get back to here. Okay, so I'll talk a little bit about some latent variable learning and so forth as we go. We've looked at this for lots and lots of different applications. So this is just blatant advertising with lots of my students and postdocs' last names. I'm not going to talk about any of these today. But what I want to do instead is show you the keywords so you can come find me later if you're interested. And also talk about a common challenge that came across all of these tasks. So while we do applied work in the group, we also look at sort of core parsing and learning algorithm issues. And the best issues to address are the ones that show up in lots of applications, right? This is really a pressing problem that we need to solve. And the particular pressing problem that I want to go into is the fact that we're relearning from scratch for each new domain. So we'll typically not be able to use very much of existing models at all. And if you know anything about NLP, you might find this counterintuitive. So there's things called parsers, for example, that do grammatical analyses of sentences. Why can't we reuse those? Why is it we have to relearn from scratch for everything? Okay, is the question clear? And I'll show you this from an example of an actual project we did 2 years ago. So the models have gotten a little better since then, but they're still very challenging. And in this project, what we were trying to do is take a cooking recipe and convert it to a graph representation where every node is an action and the edges model the flow of objects in the real world as you do the recipe. Okay, so this is overly complicated, but you can sort of work out that this relates back to this recipe for making some very delicious meatloaf, I think, actually, in this case. Okay, if you eat meat. Now, the tricky thing is, these are pretty simple sentences in cooking recipes, right? So you're thinking like, okay, if I took an off-the-shelf parser, it should just nail this, right? They're pretty short. They're not too complicated. There's not a whole lot of scoping ambiguity and other things you see in parsing. But it turns out it was an utter failure. I mean, the models were so bad that we had to start from scratch, and we could design an unsupervised learning method. We can get a lot of unlabeled data here, and we could get a better analysis than we could do with off-the-shelf parser.
So by parsing, you just mean computing a parse tree or something?
OK, good. So I'm being a little vague about parsing. For now, think of it as a spanning tree that's roughly representing the syntactic or grammar structure of the sentence.
Yeah. I'm just wondering, there's no notion of like semantics in parsing, right?
Good. So I'll come back to that later, and we'll add more semantics into our parsing. So I'm a little liberal. I view parsing as both syntax plus semantics. But for this project, we were just trying to use an off-the-shelf syntactic parser just to save ourselves some work. So we would still need to build models.
Why would you expect it to work? I mean, there's no notion of semantics.
So to be clear, the point is that it's usually viewed that syntactic analysis is a prerequisite for the semantic analysis. And we'd like to be able to reuse that part and then build another model on top of it. Okay. But we'd at least like to get some benefit from not having to learn the whole thing. Get rid of some of those latent decisions and have a model that could help us. Okay, so I apologize if that wasn't clear. But it turns out to be useless. We couldn't even get any reuse of any part of the model, let alone the whole model. And there's a pretty simple reason why. And that is that parsers are trained on labeled data that's incredibly expensive to produce. In the late 90s, the sentences were labeled. They labeled Wall Street Journal sentences. Okay, there are like tens of thousands of these, and we've been running on these same sentences ever since, with some slight caveats. But as a caricature of the field, that's what's happening. And it turns out there are something like 5 imperative sentences in the Wall Street Journal corpus out of tens of thousands of examples. So it has just never seen a verb as the first word in the sentence. No statistical model that didn't have this phenomenon in mind would ever allow that. And it does all kinds of contorted analyses where it takes all those verbs and turns them into strange nouns, because cut could be like a cut of something, right? So it could be a noun. And dice could be diced something. Or anyways, the point is it gets all contorted, and it's really difficult. Okay? So I don't mean to be too harsh on my own field. Parsers are very useful. But there's an open issue of how do we do domain adaptation, and how do we get these things to actually help in practice? Okay? All right, so what I'm going to tell you today is a bit of a contorted story for how you might build all the pieces to put them together. And like a lot of academic talks, the pieces don't actually fit together yet. But I have a story, and we have progress on subparts of the story. Okay, so the story goes like this. We need some way of labeling data in those new domains. Okay, so we need to just be able to get data that we can use to train parsers. And that's a relatively difficult task. And so we've introduced better ways of getting data that's much, much easier. But the data is only going to be partial. It's actually going to be at the semantic level. And then given some sort of semantic supervision, we're going to train latent models of syntax and try to train full parsers. So we have this hard latent variable learning problem like we saw before. And then in general, once we can do that sort of latent learning, we just want to build the best parsers we can. So we're going to get better and better parsing models. I'll tell you about a cool thing that we had last year on that. And finally, once you've got this whole learning pipeline running together, can you be more clever in the style of this workshop and actually pick particular examples and particular sublabels so you don't have to do a full exhaustive labeling of everything? Okay? And these two I'll go through relatively quickly. Building the fast and accurate parser, I'll do a deep dive because it's a fun algorithm that looks it's an A-star search algorithm that's at least vaguely related to reinforcement learning, and hopefully people will find it fun. And then here I'll go into less detail, but it'll be pretty directly related based on the data aspects, as I already said. Okay? And please stop me and ask me questions. I really appreciate the questions as we go. Okay. So the first thing I want to say is to teach you a little bit about a particular kind of semantics that's super useful for these sorts of systems. And this type of semantics is called semantic role labeling. And the key idea here is that this task is given a sentence, find all the verbs. And given the verbs, find all of their arguments. So for example, here we know that there was some increasing, that the agent was this pronoun. The patient was the thing that was increased. The manner was, how much it increased and so forth. And so roughly speaking, if you can do this kind of semantic analysis, you've solved some percentage, maybe 70, 80% of those other tasks that I was showing you earlier that I really care about. It's super useful to start with this rather than starting from scratch when you're doing your full analysis. Okay? Now, there's a lot of tricky things in doing this kind of annotation. So you may not know exactly what edges you want to include or exactly what labels you want to put on those edges. There have been different proposals for that. So there's something called FrameNet, where they have a very large set of possible labels. Something called PropBank, where they also have a different large set of possible labels. And these are sort of ontologies, and they predefine all these things. And then they go through and define an annotation spec, either on top of syntax, which is also very difficult to label, or in a more lax way in this case. And in general, roughly speaking, I can't possibly teach all this to you in this time, but roughly speaking, doing this kind of annotation requires an undergraduate degree in linguistics, requires you to read hundreds of pages of annotation spec, and takes months to learn how to do well. Okay? All right. So that's okay. And actually, I read those manuals. They're fun to read. I learned a lot about linguistics by doing it. But it's just it's a data bottleneck issue, right? There was a lot of really interesting analysis. Those are important things. But the question we asked is, could we do a bit less? So could we come up with some lighter form of annotation that from the perspective of training parsers for the kind of tasks we care about is effectively as good, even if it's noisy, even if it makes the machine learning problem a bit harder, and then we can push forward from there. Okay, so is it clear, the setup? And I think we mostly succeeded. And the reason I think that is because I can train any native speaker in a few minutes to do it. And so I'll just train you all right now, and then you can start labeling data for me, okay? So that's the idea. So let's go back to our sentence here. I show you a sentence, you're the labeler. I highlight a verb in that sentence. And then I ask you to write question-answer pairs in natural language, in English, okay? And what I stipulate is the question needs to include the verb, and the answer needs to be a phrase from the original sentence. Okay, so you're going to write both the question and the answer. It's a little unintuitive that way. And you're going to write as many of these pairs as you possibly can. Okay? So for example, here you might ask, who increased something? It's a little weird to answer with the pronoun, but you don't have the full context. So that's the best you can do. And you would repeat. So what is increased? When is something increased this year? And so forth. And Lu Heng He is a PhD student. She's amazing that let this work. And she also did some of the later projects. Okay. And so what we did, I guess almost 2 years ago now, is we sort of had a whole paper where we went through this kind of an annotation scheme, and we argued extensively that you're getting almost the same kinds of information as you got in those much, much more detailed annotation schemes that I was sort of hand-waving about earlier. Okay, here's another example where, again, for comparison, we did a lot of Wall Street Journal sentences so that we could compare to the existing stuff. And you get sort of analyses like these with lots of different prepositional phrases attaching. But the beautiful thing about this scheme is that anybody can do it. If you understand the text, you can do this scheme, and you can start gathering data.
So would the answers be used to fill in one of these, the FrameNet frames or something like that?
Yeah, so that's a great question. So how would we link this back to sort of the FrameNet or PropBank that we saw earlier? So mostly we've just kind of argued it's a new alternative. But there is work on kind of jointly embedding all these schemes into kind of the same space and pooling data across the different approaches. And I think that would be really interesting. In some sense, because we're using these natural language questions, we haven't taken a principled stand on whether this is an agent or a patient or these sort of ontological distinctions that linguists often make. So we are labeling less than they're labeling. But for the perspective of parsing, you're getting attachment information. You know kind of what should attach where. And that's kind of what we need. That's one of the hardest parts for building these systems in practice.
So in terms of doing this, though, there is some degree of flexibility in how I actually frame these questions. Like I don't have to follow a particular format, but they are who, what, where, when.
Exactly. And we did actually, in practice, to make it a little easier, that we provided a templated class of possible questions to the annotators. But you could relax that. And that's why you're seeing these weird, like someone and some things, because we were trying to give them some templates to follow. It was slightly awkward. So we went out and we gathered some data. We hired people to do this annotation for us. These are not meant to be super impressive numbers, only to say that we've done it at a big enough scale to kind of know that it works. We did it both on the sort of Newswire, Wall Street Journal text, as well as some Wikipedia text to show that you could do it more general domains. And costs were modest. So we're looking at something like $1 per sentence. In contrast, other annotation schemes have, orders of magnitude more cost. Okay, so it's hard to really quantify, but this is at least something that we could quantify here. And in general, it didn't take that long to do the different sentences for the annotators, which is, correlated with the cost. Right. So, there's probably one or two people in the room that know what this left column means here. But those are a set of labels that would be used in one of these alternative tasks. And so this is a confusion matrix between RWH words and those set of labels. And what you see is although I could have sorted it so that it was actually on diagonal, you're getting these sort of interesting things. So whereas they would have marked something a location relationship, we tend to get the word where, so forth and so on. But it's not a perfect correlation. Like our data is a bit noisier. And that's because there is aliasing. There is word sense problems in English. We have all these problems. But nonetheless, we've got a pretty good signal. And the question is, what can we actually do with it?
Are you asking people to do the same sentence, or are you just doing one set of questions per sentence?
Yeah, so we did. I didn't include any of the inner annotator agreement numbers here, but we did all the standard stuff of kind of getting 5 people to do it and looking at their agreement and seeing how they differ. And the agreement is pretty high. The thing that will vary is the exact wording of the questions. Like maybe they might do an active-passive alternation or something. But in terms of the edges that exist from the question-answer pairs, you get good agreement on that.
So I'm seeing this AM-PRD. Like, you got very few of those. Is that something you cannot really express with one question?
Yeah. There are some particular cases that we're not getting right. That's right. And I actually don't remember exactly what AM-PRD is. And it's something we could talk about more later. I can go look it up. So it's not perfect, but it's good signal. OK. So in summary, again, I'm kind of doing the first 2 sections pretty quickly. We've got some way to get this data. It's not perfect. It's only for verbs, not all of the structure of the sentence, but it gives you a lot of signal. And it's something that we really want to push, and scale up and get these light annotations. Okay. Now, given that we have these kind of light annotations, what the heck are we going to do with them? Right? So we want to build parsers that do really detailed analyses of sentences. Can you train a parser from just that light supervision? We still don't know yet, okay, because again, this is kind of vaporware. But what we did is actually look at PropBank, one of those other alternatives that was more carefully done, and showed that at least from that supervision, you can train a parser. Okay, so we still need to do the little bit of extra work to show we can handle the noise. But given a similar kind of supervision that's a bit cleaner, it does work. Okay, so I'll take you through that story now.
So could you define what's, just a title actually. So what would be success for broad coverage semantic parsing?
Yeah, so it's a good question. So it's a good question. So if one semantic parsing you could imagine is any model that produced some sort of semantic representation of the text. So if you think about these predicate argument structures that we were looking at back here, that's a semantic representation of the task. So I would consider it success if any sentence you handed me, I could produce the right edges for it.
And what's the success rate right now?
It depends on the domain. So in domain, like if you match your training, it would be in the low 80s. Out of domain, it could be as low as the 30s. I mean, it just really falls apart out of domain. And that's kind of the motivation for why we're going to get, one way to make it work out of domain is to get a little bit more data, train some extra models from it, and figure out how to do domain adaptation well. Yeah, those are great clarification questions. I'm sort of more used to an NLP audience, so I really appreciate that.
Yeah, maybe they actually know that that number is very low.
No, that's great. That's really great. Okay. All right. So again, I'm going to give you sort of a cartoon view of this and go through this relatively quickly, and then we'll do a deep dive on some parsing algorithms. So it turns out that it's actually pretty tricky to get this sort of semantic relationships right. So this is this arg0. This might be like a who question, right? That's under that different labeling scheme. And the reason it's tricky to get something that's more semantic rather than syntax is because it can have an arbitrary long-distance relationship between the surface forms of the words. So here we say John denied the report, John refused to deny the report, John refused to confirm or deny the report. It's the same relationship in every case, but I can construct sentences where it's sort of arbitrarily convoluted and far apart. Whereas a syntactic representation that you would typically build with something like the Stanford parser does all these sort of local edges much more commonly. That doesn't include these longer distance semantic relationships, and that's the crucial distinction of the kind of information that we're trying to get. But it also introduces a real sparsity challenge at learning, because at test time there'll be some convoluted path that gets you between the two things that you've never seen before. and you need to be able to correctly predict that semantic relationship.
Ultimately, would you also be interested in like looking at the entire paragraph, not just sentence?
Absolutely. And integrating with co-reference resolution and resolving pronouns, but this is kind of where the state of the art is right now.
Is it understood like what fraction of sentences do you need the context information for?
It's a good question. So if I understand the question correctly, I could analyze this sentence in isolation, or I could analyze it within the context of the rest of the document. There are very few models that do it within the context of the rest of the document. And again, at least in domain, we're doing pretty well in terms of numbers. Nobody really knows how much the context would help. Somebody might get mad at me when they hear me say that, but that's my opinion at least. And I've never seen any careful numbers on that.
No, but like, is it like 10% or is it 30%, 50%?
Well, I mean, in domain, you're getting 80% anyway, so it's not, there's not 30% left, but yeah. My intuition is that the biggest problems are like world knowledge and knowing like what verbs can go with which nouns rather than the context, but we don't have careful numbers measuring that.
And if you ask people to do this in a really different domain they have no expertise on, are they worse? Like, are they significantly worse with this? Or?
Yeah, so for the data annotation task from the last part, you need to understand the text to be able to answer the questions, right? Although we actually ran some biomedical text from PubMed through crowd workers. I'll talk about that the very last part. And they were able to do it. They didn't know what any of the nouns meant, but they kind of got enough information from like the overall structure of the sentence that they actually were able to improve the parser, even though some of them might have been biologists in the crowd, but I suspect the average crowd worker is not a biologist.
So like, we do have a much more general parser than what
Yeah, that's it. Thank you. Okay, and so what people have done is they've decided to say, okay, let's do some joint models. So let's jointly model this syntactic information and this semantic information. Let's build a distribution over both jointly or do it discriminatively, however you want. And hopefully that should improve performance. And here is a graph where I've purposefully hidden who did which result, but this is all a different paper. And purple are the joint models, and green are the pipeline models, where you would first build your syntax and then build your semantics, those longer edges on top of it. And it's been notoriously difficult to get joint reasoning to actually help in this setting. So it's much better just to fix your syntactic model and then do your semantics on top of that. Not entirely clear why. Probably because the semantic gets harder, and so when you reason about it jointly, you go back and mess up some of those syntactic decisions that you could have just fixed in a pipeline approach. Okay. And so 2 years ago, Mike Lewis, who is a postdoc in the group, came up with a way of solving this and getting a joint model that actually works better. If I was giving this talk to an NLP audience, very few people, this particular parsing formula is called CCG, and even an NLP audience, very few people would know what it is. So I'm going to keep it at sort of a caricature level. Not very few, but know all the details of it. Of course, they would know what it is. Keep it at so much of a character level, which is to say, rather than having sort of an algorithm that does syntax as a spanning tree, like I was showing you before, we had those labeled edges, we're doing a much more detailed syntactic analysis based on linguistic theory. And this linguistic theory is categorical grammars, combinatorial categorical grammars. And the main thing that this theory does is it does a tree-structured analysis, but as it's doing that tree-structured analysis, it builds a graph-structured set of dependencies. So in particular, when you get these kind of verbs like wanted that project down, so the fact that wanted is here means that John should not only go with wanted, but it should also go with confirm. Okay, and so the grammar has a really worked out theory of when you should project those extra semantic edges, and it has special mechanisms for projecting them arbitrary long distances. Okay, and that's kind of what you could see if I actually unpacked all this analysis for you here, which I won't. But the take-home story is that this grammar is typically thought to be harder to parse with, although in the next section I'll show you that's not necessarily true. You can't just directly apply a spanning tree algorithm or something to do the parsing. But we actually have really great parsing algorithms for it, and it does a much more detailed analysis. And the cool thing is that if you do this analysis, you get out a set of syntactic dependencies that directly correspond to those semantic edges that I wanted to do before. And then doing semantic role labeling jointly, doing that end semantic task jointly, is just a matter of labeling the edges that the parser will give you anyways. Okay, so that's pretty hand-wavy. Here's how the learning actually works in practice. If you have data that only gives you semantic supervision, so you only have those edges, this is a tiny sentence, but those could be arbitrarily long. You run your parser, and you get conceptually the space of all possible parses. Of course, we use a dynamic program here, and Mike was very clever at making this efficient because there's exponentially many of these in the sentence length. So there's a real contribution of the work. You notice which ones actually got the right semantics, which ones didn't. And you optimize for the marginal likelihood of the ones that actually get the semantics correct. I lost my highlighting there. You optimize for these two that are correct. You try to maximize the likelihood of them, and you get a training algorithm that actually works. Okay? All right, so here's some of the other previous joint model, some other state-of-the-art results. Here's our model if you run it in a pipelined way where you aren't doing that joint training like I just described. And here's if you actually do the joint training. This is in domain for the Newswire text. This kind of a gain is respectable. It's not absolutely huge, but something like a point is usually a big deal in an NLP problem. And the nice thing from our perspective is that it actually worked pretty well out of domain too. So this was on testing on biology text. I'm playing fast and loose with my y-axis, really spreading things out a bit, so pay attention to that. The overall results out of domain are still a lot lower, but we got even bigger gains out of domain. So something about modeling that more semantic information was actually very useful there. I'm not sure we have a super deep understanding, but that's sort of an interesting result.
So just to understand, so you were training on that label thing that you got people to label?
No. So crucially, we're training on so remember our labeled stuff that we got was we showed that it was very similar to the more carefully done stuff that had been done before, but that was done at a bigger scale than we did. So we're using that here. Okay, so I'm playing a little sleight of hand. Like I said, all the pieces don't fit together. These two papers were done in parallel at the same time, right? But we had kind of this story that eventually, hopefully, will all come together, and we're still working on that. Is that clear?
So CCD it was developed for exactly this or something else?
They were designed by linguists with semantic applications in mind. So they tend to do a good job of building representations of semantics on top of them. And this is one instance of that phenomenon. And there are other kinds of semantics that you can also build really nicely on top of them, including, I think, what Tom talked about on Monday. It's a reason why he would, for example, use it in his work. But it wouldn't be the exact same semantics that I'm doing here. I don't think actually came after.
So, just so I understand, out of domain means you've trained on whatever, like Wall Street Journal, and you evaluate on bio stuff?
Exactly. Thanks. I apologize if that wasn't clear. So when I say domain, I mean like a genre of text. Other questions? So my hand wavy story continues. I've shown you can get some annotations. I've pretended like I actually use those annotations. I actually use something slightly different. But it's roughly the right story, and I'm roughly training a latent model from that. And now I actually want to build really good parsers just more generally. So what I should really be doing here, if I was doing things correctly, is I should have these noisy supervision. I should be latent on top of them, and then I should be building my good parsers on top of that latent variable learning. That's a nightmare. OK, I'm not actually going to do that. That would be really hard. We'll get there someday. So what I'm going to actually do in this part of the talk is take a step back and just assume I have labeled parse trees and I'm only doing syntax. OK, so it's going to be a good parser. It's going to work really well, but we're going to have higher requirements for training it for now. So this is another place where the story doesn't all fit together yet. OK? But bear with me. I'll show you a cool result, and hopefully in the next few years we'll be able, or next, who knows, not years, we'll be able to generalize and make all the pieces fit together. OK? So what we did, this was a paper Kenton Lee had at EMNLP last year, won the Best Paper Award. And we showed for the first time how to build a parser that can have global features. So I'll define what a global feature is in just a minute. But an instance of a global feature is a neural net that builds an embedding for every subtree of the sentence, a different embedding that can depend on the entire subtree. So it has these global features or these neural net things, and then it's going to have some sort of optimality guarantees. So typically when you do a neural parser, you have to resort to greedy inference to find the best possible parse. Okay, and we're going to use an A-star algorithm that it will at least give a certificate of optimality. So you'll at least know when you got it right, although it could possibly, in a worst case, run forever. And just to reiterate, if it wasn't clear what I meant by global features, when you're building a parse, what you're going to do is you're going to start out with little chunks for the words. You're going to build them bigger and bigger as you go. And we want, when you have any subtree that you're currently considering, to be able to test arbitrary properties of the entire subtree and have no equivalence. So you can put any arbitrary feature you want on that subtree. And that's the condition that we're going to actually enforce. And we'll still show that you can get a very good and efficient parser. And of course, that's going to help accuracy. If you can learn good features, that's where the neural net comes in. The neural net will give us good global features, and the algorithm will give us some way of dealing with them and actually doing inference.
A feature, is it just a mapping from a labeled subtree to a real,
to a vector in general, sure. Yeah. That would be a feature vector. So you could think of each dimension in that vector as a specific feature. But it doesn't matter, it's fine. Okay?
Sorry, because I'm not super familiar. Can you give me like an example of what a human would do? As like, so neural nets can come up with arbitrary features. What would be like, what would be an expert saying, like, if I was doing expert feature selection for this task?
Yeah, so if the one common feature is a bilexical dependency, so is there some edge in the parse between the word fruit and the verb flies? Like, I'm going to use this sentence, fruit flies like bananas, as one of my examples. So there would be a feature that would be 1 if there is such an edge and 0 otherwise. And typically, if you design features by hand, they would be large, many features. These neural representations will be dense. Okay. I think it's feature like any sense of the word, but it's just over structures. Now, to actually build such a parser, we're going to want to go from sentences. We're going to want to produce these tree-structured representations like I showed you earlier. The reason we're using these particular structures is motivated by the kind of semantic analysis I showed you earlier. And it's useful to have this notion of a hypergraph. Okay, so this sounds fancier than it is. All this is doing is showing me the derivation structure that I took to actually build up this parse. So like I said earlier, I'm going to do some sort of assignment of the first little bits here to the words. And then I'm going to combine them into bigger and bigger pieces. So for example, this piece here corresponds to this. These two pieces can combine to make this complete parse. So this is a graph-structured representation of the derivation by which I built the parse. Okay? And the reason we want to have this formal object is it's going to help us think about how to search to find an efficient path to build a parse that's actually good. Okay? In general, to do this parsing problem, there'll be many different possible parses, and then, of course, many different ways of deriving them. In general, there'll be sort of exponentially many of these different graphs in sentence length, and all kinds of grammar constants that make it even bigger, really big in practice. Okay? One nice thing about this hypergraph formulation is that we're gonna have to choose one of these, and we're gonna build models that score them. And the score is going to be some function on this edge. So it can look at all the details in each of these nodes. Could have features on those subtrees. It could do something else. The score is going to be local to the edges. And the score for a complete derivation is just going to be the sum over the scores of those edges. So that's kind of a standard setup. Okay? And then we're going to find a derivation that gets the highest sum in total. In the final little piece here, just to get all this thing going, is that we wouldn't really build these paths separately. What we'd really do is collapse the whole thing down into one big hypergraph that represents all possible parses in a single graph. Right? So there's sort of this subpart would go to this parse, this subpart would go to this parse, and now you start to see that we're getting sharing. Right? So when you actually do this computation, you wouldn't need to rebuild those nodes over and over again for the different parses. And what you'd actually do is work directly in this one big hypergraph and just try to explore a small subset of it to find the right parse.
Is that a tractable graph or reasonable sentence?
That's exactly a great question. So is this a tractable graph? So one trick is to notice is that I have complete parses as one whole node in the graph. So there are exponentially many of these parses also in sentence length. Right? So there's all the different ways of kind of bracketing and combining things. So as defined, which I think I have a slide, the very next slide, as defined so far, this is very expressive because I get sort of all these information in the nodes. But there's an exponentially large graph, and finding the best derivation through it is not tractable. How have people dealt with this in practice? We want to build expressive parsers. We want to have all this information available. So there's kind of two ways of dealing with this in the literature. You can do approximate inference. So you can do some sort of greedy or beam search, building up a subpart of the graph as you go. Or you can do what's called re-ranking. So you use a simpler model where you can exactly build a subpart of the graph and then rescore it according to some more complicated model.
So the argmax you had on the previous slide was still under this additive.
That's right. Everything is going to be under the additive constraint.
Even though like you have combinatorily many possibilities, there's a lot of decomposition.
That's right. That's right. But, and I'll show you in a second how to get that and turn into a dynamic program that's efficient in just 2 slides. But you're exactly thinking the right direction. That's exactly right. Okay. All right, so that's one possibility is you can give up on exact inference. Another possibility is you can redefine this graph to sort of further collapse those nodes and assume that a lot of nodes are equivalent. So for example, in each node, you can only store the root of the analysis and the actual words and not all the details of exactly how you got there. And if you do this cleverly, you'll get polynomial mini nodes in sentence length, and you'll get exact algorithms like the CKY parsing algorithm out. Okay, so I'm not going to reteach you all of this, but this is to give you the context of how it fits into the bigger picture. So you'll get efficient inference, you'll get polynomial mini nodes, but again, remember we're doing these edge scores, and you'll have much less information available to your model. So these are sometimes called local models, because they don't get to know the entire parse structure, they only get to look at little subparts of the analysis, and that's why that's the dynamic programming signature, and that's why it's actually efficient in practice. So we have this trade-off. Is it clear? And it's going to break these sort of dynamic, the neural nets or the global features, because for the global features, I want to look at all this information in these nodes, and I want to maybe have a different feature depending on how I got there. But that information just isn't stored in these efficient algorithms. So there's this fundamental trade-off in terms of what you do. So here's the trade-off a little bit more succinctly. In this global model, we can do very expressive scoring. So this is that sum over all the edges that we saw. We can have a very expressive score, but we have an intractable inference problem. In these more local models, we have efficient dynamic programs for doing the parsing, but we have limited expressivity. So we would expect the accuracy to be less. And our result here was to show that actually these two things are not incompatible. So I'll show you in some amount of detail exactly how this goes. But somehow we're going to combine those two models I just showed you earlier to get a very expressive model. And then we're going to use an A-star search algorithm to make it actually quite efficient and work well in practice. Okay. So to do this, I have to just very quickly teach you about how A-star parsing works. So I know it's late in the afternoon, and bear with me. Hopefully many people have seen the A-star algorithm, and many have taught Intro AI. It's a pretty straightforward application of it. And then I'm going to show you how to do a really efficient A-star parser in a local model. And then I'll show you how to extend it to the global model. Okay, so we're going to go through these steps pretty quickly, but stop me if parts of it aren't clear. The search space for the A-star are these partially built parses. There's those nodes in that tree. And so we're going to search through the space of all partial parses, building up bigger and bigger parses as we go through the analysis. And we're going to have some guess to get A-star to work. As you may know, you're going to have some guess about how good things could possibly be in the future. So we're going to have to guess, if I completed this parse, how good could it possibly be? More formally, you have this scoring function that orders the order in which you do the search, and that decomposes into two pieces. How good is the parse so far? I've been hand-waving about global features and neural nets. I'll be more concrete about that later, but that's where that comes in. That's that edge score for everything you've built so far. And then some sort of upper bound on how good things could possibly be. So that's your heuristic. It says no matter how you complete this parse, you couldn't possibly do better than this amount of extra score. So we know how well we've done so far. We know a bound on how much the score could possibly improve when we complete the parse. And then we just literally search through this graph in the order of that function f. So you go through, you build out your nodes, you keep adding bigger and bigger nodes as you're going. And in the end, when you actually get a complete parse that comes off of this is a priority queue or an agenda, the complete parse that comes off, everything that you didn't expand is provably worse, because you had that bound on how good it could possibly be later. Okay? And that's A-star parsing.
Has that been done before, or is that something?
So A-star parsing has been done before. And the contribution here was, we had sort of two contributions. One paper, Mike Lewis showed how to do it for CCG. A particular way of doing it for CCG with neural models that works well. Actually wasn't the first time for CCG. And then we're the first to do it with these global features like this. Okay, so we're the first to actually work on this version of it. All right. So just to now complete the story, the details of exactly how you do the bound are going to depend on exactly how you score how good a parse is, right? So depending on the scoring that you actually provide, you're going to need a different way of doing the bounding. So there was an interesting model that Mike Lewis came up with last year, where this entire structure, the entire parse, is scored by just scoring how much you like each of these first four steps. So the score of a complete parse is the sum of the scores of the individual syntactic analysis that's assigned to each word. You can think of this as like a part-of-speech tagging problem, if you know, or some other tagging problem in NLP. So it's a very strong assumption. All these later decisions don't matter at all. And the only thing that actually matters is how you tag those individual words. Okay? It's unintuitive that this should work. It turns out you can get a state-of-the-art parser by doing this. I showed that in 2016. It's a very strong locality assumption about what actually matters. I encourage you to go read that paper if you're interested. But from the perspective of this story, it's just some way to put all the pieces together. So if we have some partial parse, well, we know how good this thing is so far. That's just the sum of those word assignments. And then we can get a pretty trivial bound on how good everything else can be by just independently taking a max over everything you could assign to those particular words and summing them up. Right? Because the sum of maxes is going to be the same as it's going to be a bound on the individual scores you could get. Okay? And that gives you a complete algorithm. So at this point, you know how to do A-star parsing in the case where we made a really strong assumption about scoring, and then we built out a full and complete algorithm.
Sorry, what was the assumption about scoring?
That the score for a parse decomposes into the sum of the score of just those assignments there. And that was crucial for deriving this bound, right? Because I said you're going to independently do a max. That's only a bound because of this assumption I made about the sum here. Is that clear? I'm going very fast, which I realize. Okay. Now, the real challenge, if you want to do sort of global features, is how to not make such a strong assumption but still get a bound, right? So we want to, the assumption that you only depend on these little subtrees is totally incompatible with looking at arbitrary aspects of this, right? We can't pay attention to anything after that initial decision. So what we need to do is somehow come up with some sort of trick. We're going to use a fancier method, sort of an arbitrary, really complicated neural net for actually building representations and scoring different subtrees. But then, if you're doing this arbitrary scoring of subtrees, that neural net can care about any different aspects of how this is built and any aspect of how this combines with what you have yet to do. So it's very unintuitive to think about how you could come up with a bound in that setting. Okay? And, in some sense, we did a sneaky trick. So we didn't come up with a deep bound, and we came up with a general method for very loosely bounding it, but somehow made it actually learn to work well in practice. Okay? So I can show you how this bound works. What we're going to do is we're going to have that neural net or that global feature compute some score, and we're just going to constrain its score to be negative. Okay? And so if it's negative, we know a very loose bound. Yeah, all the theorists in the room snicker. I told you I was not a theorist at the start of the talk. The bound is 0. Now, the tricky thing is I could actually run this. This is well-defined. This is an A-star algorithm, but it would work horribly, right? Because that would be a super loose bound. The model is going to make all kinds of distinctions. The score is going to be all over the range, and that's not going to work well at all. So we have this observation that we had this good local model from before that actually was a state-of-the-art parser. It just couldn't make certain distinctions here and there that it needed. So what we're actually going to do is sum in that local score that I just defined for you that only looked at those the word level choices, along with its good heuristic, that reasonably tight heuristic of the max. And we're going to just combine these together. So our actual heuristic will be a sum, our actual score will be the sum, and we're going to pre-train a local model, and then just train a global model that goes and fixes the mistakes that it made. It goes in and fine-tunes its decisions. And then we'll get a very efficient parser in practice. Okay? That's a lot in one slide going on there. So we have this trade-off where we're going to build on top of a parser that had a really good A-star algorithm but made unrealistic assumptions. And we're going to allow ourselves to look at arbitrary aspects, but focus, because we know we only have a loose bound, and try to focus that learning. That's the interactive aspect. We're going to focus the learning on only making the corrections to the local model that it needs to make. So in the interest of time, I'm going to kind of skip all the details of how this neural net actually works. It's a pretty standard architecture. We've got this bidirectional LSTM and then a feed-forward up above. And we're sort of taking best practices from the NLP literature, but figuring out how to do it in this setting where we're getting this more detailed analysis and some sort of optimality guarantees from the A-star. We changed the activation of the neural net, so you can just use a log probability activation. That will enforce that it be negative. You can backprop through that. It's differentiable, no big deal. It's pretty easy to get a model to only predict negative numbers. And then the real challenge is actually how you do the learning. So how are we going to set up this learning scheme so that we're able to fine-tune this local model and just correct the predictions of use this global model to fine-tune the predictions or correct the predictions of the local model. And here's where, if it looks anything like reinforcement learning, it would show up. So what we do is we say, OK, we've got this good local model. Let's parse with it. And let's just correct the mistakes it actually makes in practice in an online fashion as you parse your data. OK, so you just run your agenda. You get out these things. And if it's ever the case that you would have popped something off of your agenda that shouldn't have been in that gold parse, we'll call that a violation. And we'll just define a loss function that tries to minimize violations. And we'll make sure it's differentiable. We can backprop through it. And we'll have a well-defined learning problem. So I will skip over a lot of the details here. But the idea is that we'll look at all these violations that happened. We'll have a pretty straightforward way of just saying, look, all the stuff that is consistent with what you should have done, that's good. That subtracts from the loss. All the things that you were predicting when you shouldn't have, that's bad. That adds to the loss. And it's a pretty straightforward overall setup for doing the learning.
Like, do you say run A star all the way to the finish, and then you get all of the violations, and then you retrain your global, or do you retrain it after each step?
So it's a good question, and I didn't specify that level of detail. So you run it all the way through, you collect all the violations, and then you do an online update for that one example, and then you go on and parse the next example. So there's sort of a bit of a flavor. Again, this is not a stochastic environment or anything, but you're kind of learning as you go through and try to actually do things.
Isn't that super, like, I would have thought with the neural net, like, incredibly computationally?
Yeah, so it's not as bad as you might expect computationally. You do need GPU. Actually, this is not running on a GPU because it's a dynamic network. The Kenton who ran this project is a very good engineer. He was able to build it out. It runs fine. Yeah, so there is a wrinkle here that I don't have slides for. Sorry that I paused. There's a wrinkle here I don't have slides for, which is that they had to do a little bit of cool setting up of the backprop so that you would actually use the hypergraph and reuse the gradients as you backprop through the hypergraph after you do your parsing. So you don't have to recompute the gradients for every possible analysis. So basically, they're doing backprop on that hypergraph, not directly on each individual parse. And that was absolutely crucial to get it to work. But I'm already massively over time, so I'm just not even going to try to go into that, unlike the other things that I find exciting. But it is in the paper. It's a cute trick. OK. All right. So that's it. The form of updates I showed you are super aggressive. So we didn't really have to stop and do an update the first time we popped something. I mean, this is an A-star algorithm. It could keep running. It would recover from that eventually. It will eventually get the right parse modulo time constraints. But it was specifically chosen to aggressively try to force the algorithm to be as efficient as possible. So we really prefer it to never explore anything it didn't have to. And the paper does some experiments of different versions of that. And it's kind of an interesting design point. OK. I will mostly skip the details other than to say we actually got a new state-of-the-art result by a modest amount. And it was the first time that you've had these sort of global properties with any kind of understanding of optimality. And in practice, the certificate of optimality you get from A-star is almost always there, 99.9% of the time. So we do know that we're finding the right parses under the model that we've learned. And the really shocking thing from my perspective is there are literally exponentially many parses for any sentence. I mean, it's huge. It's this nasty thing. That's why people did dynamic programs. And this model, when it runs its A-star, only pops 190 things off the agenda on average for each sentence. So it really just kind of hones in on the right analysis and just goes to crazy and just zips it right out. And that's a shocking result to me. I would have never guessed that this number could be that low. And the average sentence length here is something like 35 in this corpus.
So after your global model converge, so
Yeah.
maybe so it's sort of like at the beginning you're keeping to update your global model, and then after a while that's static, and then you're just doing A-star for any these.
Yeah, I apologize. This is after learning. And these numbers would be worse during learning. Absolutely.
So how much is the improvement over the basic local model that you start from?
I don't have that number on this slide, but the local model can always get the optimality because you can do a dynamic program if you want to manage the agenda because it's a local model. And during early updates, the local model, or the early model is much less focused. I don't remember the exact number, but it would be orders of magnitude more that you'd have to.
More in terms of performance?
Oh, I'm sorry. So this column here, I'm going too fast, is the local model. So I did at least have that on the slides. I apologize. Jacob.
If you do agree to decode here, given that you already explained.
So here's the greedy decode results. Various approaches. We get a modest, again, even more. These can learn those global features, but they do greedy inference as opposed to our exact inference. We do mildly better, which is a little bit better than them. As you know, so the greediness isn't actually hurting performance, but it's actually much slower. So this focusing behavior of the algorithm actually makes a faster parser than a greedy algorithm, which is cool. You explore a lot less. Okay. And I am already at my 45 minutes, so I have a whole nother bullet to go. So let me do this at sort of a caricature level, just go about 5 minutes over. And then, of course, you can stop me and ask me questions. I'll go 10 minutes over. That'll be awesome. Okay. All right. So where are we? We've talked about how to get semantics. We talked about how to do the latent learning. We talked about how to build cool parsers with various guarantees. I wish all that fit together. Maybe it will someday. But now, in the theme of this workshop, I actually want to say, let's go back to this issue of getting the semantics. And let's say, could we be more focused? So think about those question-answer pairs. For any particular sentence, I told you how to exhaustively get all the question answers. You just have somebody write them down. Could we instead very carefully pick a few questions to ask the user? And given that we're asking those questions, could we actually use a parser to make them multiple choice questions? So they don't have to write the question. They don't have to write the answer. They just read the question, pick the correct answer from the set of options, and we should be able to use that signal to improve the parser. And we've shown that's possible, although gains are still modest and there's more work to be done there. So our key hypothesis is that we want to really make this crowdsourceable and scalable. Here's the example. Pat ate the cake on the table that I baked last night, somewhat convoluted. But I think that any of us natural language processor, human language processors would know what was actually baked. It was not the table, right? I think. OK. Parser would often get this wrong. They'd often think that you're baking the table. This is the kind of world knowledge that I was talking about earlier when we were talking about would context help. World knowledge about what can be baked would help a whole lot more. Okay? And in a very general sense for every word that could possibly show up.
By the way, also some common sense, right? Because you could bake a table, you paint it and bake it.
Good. So when I use the word world knowledge, you could just replace that with common sense. They're the same thing to me. And absolutely, yeah, that's what I meant. Absolutely. Okay. So the parser might make some mistake, but of course people could actually, very easily make this judgment. Can we set up a scheme where we can put this in front of people and get their judgments and improve the parser? Okay. So what we're going to do is we're going to actually run a parser. It will be actually specifically the local model from the last section. So it is a state-of-the-art parser at the time this work was done, pretty close to the one I just taught you. And we're going to get an n-best list out of it. So we're going to have the top n analyses that it thinks are correct, along with a probability of each. Okay? And then we're going to look for confusions where the parser isn't sure, should that actually be going to table or should that actually be going to cake? And then based on those confusions and that uncertainty that the parser has, we're going to automatically generate a multiple choice question that we can put in front of a user and get a judgment. And hopefully they'll answer it correctly. And hopefully we'll be able to use that to improve the parser's performance.
Maybe this is a dumb question, but we had word embeddings somewhere before. If I have word embeddings, I would know that bake and cake are much more similar or related than bake and table. So couldn't a machine predict that question?
Yes.
Or is this just a...
So this is a toy example. I haven't run this through the parser. I don't know if it would actually get this example right? But this kind of confusion where you have some verb and you're not sure what's argument, especially in those longer distance things where they're going back up like I carefully constructed that sentence, is a classically very difficult problem for a parser. And we use state-of-the-art word embeddings in all the neural parsers, and they do not, word embeddings don't magically solve the problem. They're very useful, they're kind of semi-supervised learning, but you really need world knowledge in general, you need common sense. And this would be one way of injecting it actually by getting judgments and trying to shove that back into the model. Okay, if we could do it at scale. Okay, so I will mostly I will extract out all the details and say here's how the pipeline works. We run the parser. We get these confusions from that n-best list. We have a set of heuristics. Okay, so this is not a machine learning approach. You might shudder, but we have a set of heuristics for going from that n-best list to an actual question with some answers. We run that through a Mechanical Turk. We use the judgments as extra soft constraints that we inject. You could think of these as extra features that the parser gets. We reparse with those soft constraints, and we hope that we get a better result. In a dream scenario, when we designed this work, you would hope the result would be so much better that you could then take the original parsing model, that neural net that I taught you, retrain it on that data and get just a better parser. Sadly, it did not work that well yet. Okay, so this is a hedged result, but we were able to improve the parsers, so we showed that this is kind of worthy of future study, although we didn't, get quite as big of a result as we were hoping.
When you retrain that, what?
So we don't retrain it.
It would be a strong function of how many of your sentences had this kind of trickiness character. Were you retraining on a normal set of data that didn't have too much of this, or did you have?
So I'll tell you the detail of why it didn't work in a second. But roughly speaking, we were able to get some really hard sentences and get them to get better analyses. But it was only about 10% of the data that we changed at all. And so there's a real issue of how do you actually get this heuristic question generation to get enough coverage to actually improve enough of the data to get the distinctions you want. So we showed it's possible, but we weren't getting the coverage we needed to actually get large gains. And I'll show you that on the slide in a second. Okay.
And so you're selecting which sentences, and then also heuristically picking some questions for those selected sentences.
Okay, so we're picking which sentences, which questions, and the set of answers, and then we're putting that in front of a Turker.
So you have this bullet that said not retraining model?
Yeah.
So what does that mean?
So that's what I was just trying to explain not terribly well, which is that if you did a good job of this, after you do the reparsing, okay, this uses the human supervision to get a new analysis for the sentence. If that analysis is better, that could provide a new labeled training example so that you could run that on some unlabeled data, get new trees that way, retrain the parser on those new trees, and you'd have a better parser. But we weren't able to get enough gains to actually do that. We showed improvements, but it wasn't enough. So we did not retrain the parser. We used only a human-in-the-loop parser. We were improving its performance by asking the crowd to give it judgments. It did perform better, but it wasn't good enough that we wanted to put the effort into retraining the parser.
Test data. You don't propagate this feedback.
I'm not sure how to answer that because we didn't do it, so it wasn't on any data. But the gains that we measured when we don't think they were big enough, that was on dev and test. Yeah. And we actually did it based on dev. We only ran on test once. But anyways, yeah. Okay. So yeah, good. These are great questions. I apologize, it's not clear. Sort of different, lots of different types of audience people in the audience. Okay. Okay. So I will mostly skip over details because I think you've got the story now. These heuristics look at actually properties of these CCG grammars that I care so dearly about. And based on properties of that grammar, you can basically come up with tuples like I was showing you the examples. And then you sort of collapse those tuples. So one particular analysis from the parse would look like this. One particular analysis would look like that. And then we have a number of different scores where we say, OK, do we think the question is actually grammatical and able to be answered? What's the entropy over the set of results? So if I got the correct answer, would it actually help? I mean, I want to ask a question that you know the answer to based on the parse. And various factors like that. And we combine them all together to get a score. And that drove our actual annotation process. Okay. So then we actually got this simple task. We'd show them a sentence. We'd ask the question. And then it was multiple choice. So they could pick multiple answers. And I'll show you in a second. Sorry, it was a checkbox. So they could give you more than one correct answer. And I'll show you in a second some cases where that helps. Here's roughly the scale that we did things at. It was pretty fast. It was pretty cheap. And that was the nice thing about the multiple choice questions. I actually did include the inter-annotator agreement. It's very high. If you just think about absolute majority out of 5, we would get about 90% agreement on the questions. So people can really do these tasks. And we saw a sort of interesting phenomenon when we actually do it. So I'll just show you some phenomenon and then actually end with that. So we were able to get these long distance dependencies. So here we said what wasn't, what didn't, who. We actually, this could be who didn't elaborate something, and they're able to actually correctly pick what the parser is able. This is a challenging thing for the parser and would probably make a mistake. This is like a more real world version of the baking the table example. Actually works. In coordination, you often get multiple correct answers. So if you have a coordination, then you can get two correct answers to the question, and the annotators can actually pick that up, not perfectly, but good enough that you can actually figure out those attachments. It's a classically hard thing in NLP. But then there's some tricky challenges. So in co-reference, the sort of local attachment would be this phrase in the sort of syntactic analysis, but the annotators actually give us the antecedent of it from a co-reference chain, and so forth and so on. So I'll skip over some of the other examples and just say this is the point that I was saying to Tom earlier, which is that we got some gains.
If you wanted to use that though, to do a task, that would be okay, right? Because semantically, that's fine. Like whether you're using the proper noun or you're using the description, and then you want to make a decision based on that, that would be okay.
Absolutely. And the question was, wouldn't that be okay if you got the antecedent instead of the referring expression? The answer is yes, for an end task. So for the stuff at the beginning of the talk that motivated all this, that would be fine. For improving the CCG parse, it would be a disaster. So some of the reason why we didn't get this to work was because we were trying to improve the parser itself as opposed to looking more at end tasks. And that's a direction, that's one way to actually get this going, is to care less about whether we've improved the parser and more about performance on end tasks. And that's actually, I think, the right answer. So I think that's a really good insight from the question. Okay, so we've got some numbers. This is this experiment where we actually had Turkers look at this sort of biological or biomedical text, and they actually got us a gain there too. Our biggest gain came there. It's over 0.5 point. That's something in parsing, but they were not dramatic gains, but it showed that it worked. And then our error analysis was really kind of teasing apart what happened, and we only changed about 10% of the sentences. So our heuristics that we had for generating the questions, they just aren't general enough yet. But on the 10% that we changed, we got pretty respectable gains. So when we had an opinion, we were getting it right. We just weren't changing a whole lot of the data. Okay, so that's kind of where things stand on this project. But in the sort of theme of this workshop, I think we're going to keep working on this kind of stuff. We're going to keep improving it. And it raises all kinds of questions about, we were doing simple heuristics for which sentences to collect. If you're targeting subparts of big structure prediction problems, how do you think about that? How do you set up that learning? So I hope I can have some fun conversations with people that are more expert on these kind of active learning kinds of issues. You can see we're sort of having a lot of fun with it, but a little bit flying by the seat of our pants and just building out stuff and seeing how it works, which I think is great. Okay, so I think I've said all of these things so far. These were all those caveats that I kept trying to add in as I was going. I just wanted to make sure I had them here in case I had, for some reason, forgotten to do them along the way. But this is the summary of the talk, and I'll stop here and be happy to take questions.
So with that last project, I think one of the sort of pieces of common wisdom about these parsing models is that even when you train them with a likelihood objective, the probabilities that you get out are not actually all that well calibrated to the kinds of errors that the model makes. But I've never actually seen anyone sort of provide quantitative evidence of that. And it seems like you can do that now with that data, right? That you know sort of on the ones that your model thought was 75% better than how often you actually get it right. Have you done those?
No, we haven't looked at that. And we did, some of the monkeying with the heuristics was dealing with those kinds of issues. But remember, we didn't really care about the magnitude of the numbers. We just cared about, was there a confusion? That's enough of a confusion that we should ask about it. But you could go back and do that analysis on the data. It would be really interesting. It's a good idea. But it wasn't sort of a critical path thing for us to get to do the study.
That was the lowest I think that you mentioned. It seems like it would be useful to do that order of magnitude cheaper. I mean, maybe it's order of magnitude than what it used to be in the 90s or 2000s, but do you have a sense of how much cheaper it needs to get?
I actually have those numbers. Yeah, so 96 cents per sentence, 46 cents. So, I guess, yeah, so it would be great to be cheaper. And I think part of that would be to ask fewer questions and have really carefully selected questions, and to also look at the right subset of the sentences. And so I don't know how to do that, but I feel like that's a really exciting research direction. Just for context, if we could actually label sentences for 50 cents each, we could get like 2 orders of magnitude more data than people have right now already. And we're already training deep neural nets on like tens of thousands of sentences. So I still think this is a super exciting point to be, even where we are now. And I think it's also super exciting that there's hope to go much further because we've done such simple things so far. But it's a great point.
Think about if you find a mistake from your model, having the crowd like generate other sentences, which are to see if you can really get your head around the mistake and simpler sentences and really, correct the model in a certain family of things.
Yeah, it's a really great question. So could we use the crowd to actually generate sentences as opposed to just generating analyses of sentences? I don't know the answer to that. I've daydreamed a little bit about it. We've done some projects where we do data augmentation, where we try to algorithmically create fake sentences that would be good to train on, because always sort of data hungry in these models. It's turned out to be very difficult to do that. One reason is because if you change the distribution of natural sentences, you'll train to do well on stuff that just won't show up in actual text. So my intuition is that it should be possible to do something like that. But what we found in not exactly the same setup, but a related setup where we're trying to do it algorithmically, it turned out to be incredibly difficult. So it's possible crowd workers could solve that problem. It's also possible that they would take you off in a direction where you're kind of learning to do an artificial language and not the actual language that you see in text. So I would love to think about it more, but I don't actually know if it would work.
We heard a talk yesterday, you were here too, about the Stanford work where that involves some kind of semantic parsing like this. And one of the properties of that approach was that there was a kind of easier to more difficult sequence of training the system, right? It's kind of related to the previous question. There was a kind of curriculum of sentences on which the system was trained. Is there a role for that kind of stuff here in what you're talking about?
Yeah, so the question is, could we do a better job if we did some sort of curriculum training, maybe organizing our sentences easier to harder in some sense? I don't know the answer to that. My dream, generally the way that I've found things to work the best for the models we've done so far is just to get, real sentences that are from the distributions you care about, whether it's cooking recipes or whatever, and just go ahead and, fully label them. But then as we just talked about, maybe with this more active learning mindset, you want to do partial labels and so forth. You don't want to provide complete labels. Then maybe the curriculum learning has a story there. So maybe, if you start out with simpler things, then as you go, you're going to be more and more confident about the harder stuff, and the harder stuff is going to be more expensive to get labeled, and you'll actually win. That's quite a stretch. So in the ways we've done things so far, I don't know how to use it, but I think it's an exciting possibility to think about, and I think that in general, just sort of trying to get a parser that's better and better, and just correcting its small mistakes because it's already pretty good, and making it even better, that's got to be the way to go. Because by analogy to other fields, if we had orders of magnitude more data, you would expect these models to actually perform better. But it's so unbelievably expensive to make it right now that it's very difficult.
One more question. Several times you tried to make us believe that it was impossible to build a semantic parser for general domains. Repeatedly you would say, oh, well, you have to train it for this domain. But all of us are fairly general domain parsers. So what's your vision about how we get from here to there?
Yeah, so that's a really great question. So I don't know the answer, but I know how to take some first steps, I think. So one first step would just be to make a corpus with a bunch of domains in it and train on that, right? That's going to help. It has to help. And so that was the motivation for a lot of this QA stuff is, maybe if we can figure out how to get weaker supervision and, and the costs come down per sentence, I can just do 20 domains or 50 domains, and I could actually build that out and release it, and people would do cross-validation across domains, and they would do interesting experiments, and we would understand the models. Part of the reason why it doesn't work is probably just because there hasn't been a focus on it, and because the data hasn't been there to study it. There's a lot of smart students out there, and if you built that environment for them, I think some of them would at least make progress, if not completely solve it. And then with all the caveats about doing it cheaply and so forth. It's also possible that we just don't have the representational capacity that okay, neural nets are amazing, you're getting these really dense representations, but even that won't be enough to actually get this common sense or background knowledge into the systems. And I think that's pretty plausible, and that in the end you're going to need some external resources that also get brought in, and that you're not just going to induce it all from text. But that would be an interesting thing to try, and you could at least look at progress as you get a reasonable sized data set with lots of domains. And I don't have a good answer for exactly where that knowledge would come from, actually. I think that's a classic challenge in AI.
Don't you sort of want specializations of your parser to different domains? So like in the table example, if it's about painting tables, you want to infer that you've baked the table.
Yeah. That's good. So the question is, wouldn't you actually want a specialized model for your domain? And I think the answer is yes. And I feel kind of like a charlatan at this point. I have an answer for you too. So there's a second motivation for the QA stuff, which is that in the near term, before we can get this massive, beautiful data set and before the grad students solve all your problems, what I could actually do is provide for you a tool where maybe you work for a 3-letter agency or maybe you work for a company and you have some private data that you can't release, and you want the parser to work really well on your data. Well, I can give you a turnkey thing where you just need to get any analyst or any person that can actually understand the text, and you just need to run this procedure, and you need to make n thousand examples, or you need to do the fancy new active learning algorithm that we've released. And then at least in that domain that you care about, you'll get a good parser. And I think that would be a really cool kind of short-term goal as a step towards the one off-the-shelf thing that would actually work everywhere. And I think it's a much more practical goal in many ways, although it may be less exciting, but really important.
Building on that, maybe I feel like in vision, in the deep neural network, there's been so much more kind of transfer learning, like this big data set, you learn on that, you get these little features, and then you go into a small data set. Is there the same story here? Like when you're building neural networks, you have little features, you can do that on Wall Street Journal, and then you do it on your small domain for the next, is there that sort of transfer of features?
Yeah, so the question is, in computer vision, you can learn very general purpose representations, say from ImageNet, and then you could fine tune it, like if your images don't follow the distribution in ImageNet. It's a really cool thing to do. It helps a lot. I don't know if people are doing things like that in NLP. The other experts in the room can correct me. It's possible I've missed it. My cynical view, again, I have my one mind view at the moment is, it's again a data issue, right? So you need actually to have the data to go fine tune it in for the different domains. It's probably not entirely true. So where I said, when I set up the whole thing at the beginning with the different domains, and I said parsers never helping these domains, it's not entirely true. I mean, people do use parsers, but it tends to be a struggle. And I think the ones that get it to work well do some sort of tuning in practice. They'll go and change those parameters somewhat for their domain or adapt it a little bit, even if it's not as beautiful as like having this nice final layer that you can just backprop a little bit into. It may be a little bit more hacky in practice. So I was being a bit of a caricature there in the intro, and I think that there are things like that going on in practice, but it's not like we have this one sort of off-the-shelf accepted way of doing it. I think it requires real effort with each new domain to figure out what's going to work and what's not going to work. At least that's been our experience with the applications we've done.